I think I'm the NASA talk of this workshop, so it's very happy to do the NASA talk. So in the NASA talk, I will talk something about our latest hardware. So we call it AI Testbed, and we all have two examples for the hands-on section. So in the hands-on section, we will give a BERT model as an example to show how to train the model on our systems. And so that's where we can get started. And before we get started, you can check the GitHub repo, and there were some slides here. You can let me share it with you. So you can see all of the slides we used in the 03 AI Testbed, and you can check the slides and any scripts we were using in this talk. Okay. So now we get started. So we will introduce some AI Testbed. So I will give a little bit brief background. What happened? So just wait a moment. So we'll give a brief background of our AI Testbed. So the ALCF AI Testbed provide an infrastructure for the next generation of the AI accelerator machines. So we have the 5 kinds of the machines for the AI workload. So it will accelerate your models, and they will improve your performance, training performance, and as well they can give you better accuracy as well. So there are some 5 machines we will use in our system. So the first one is the Cerebras, the CS2, the wafer scale deep learning accelerators, and this is a very large machines. And the second one is the SambaNova, data flow accelerators, and the third one is the graph core. This is the IPU, called IPU accelerator. And the third one is the Gaussian tensor streaming processor. This one is the best used for the inference. And the last one is named the Habana Gaudi. So this machine is from the NVIDIA. Well, no, not NVIDIA, sorry, Intel. So we have all kind of machines, and if you want to know more about the machines, you can be free to check the website. We will give more machine information on the website, so you can check with them. So they will give some system overview and how to log into this hardware, and how to check the software stacks on this hardware. So in this talk, I will give 2 machines as examples to show how they design the hardware and how they design the software stacks. And so the first one is the SambaNova. So I think this machine is very popular recently. There already have a lot of papers published along with this machine, and they also have a lot of implementations with their models. So at the first beginning, I will introduce the hardware of these machines. So the first one is I will introduce the background of this hardware design. So as we know, we have if we want to run some workload on the GPU or someone else, we have a lot of parallel patterns. So the patterns I listed in this slide is we have some map, the element-wise functions, and we also have the zip. This want to reduce something together. We also have the reduce operations, which will combine all of the elements with one result, and we also have the flat map. This is also an elements-wise function, and we also have the group by function. This is used to group some values to a specific group, and if we want to run off the parallel patterns on one machine, it will be very difficult to get the very high throughput. So from these motivations, the SambaNova they design a hardware named the reconfigurable data flow architectures, the RDA. So this is the simple overview of the hardware design of the RDA. As we can see, they have some PCU. This is the computer unit, and this is the PMU. This is the memory unit, and then they also have some switch to exchanges the information from the PMU with the PCU. So and they also have the grid as the architecture. So and if you want to run the kind of the patterns, parallel patterns to this hardware, they will be very high efficient because they can reconfigurable to run the different parallel patterns to the real hardware. So so there are some basic information about what is the RDU. This is the reconfigurable data flow architecture. So as we can see, this is the chip from the SambaNova. They have a lot of transistors, and the peak performance of this one chip is about 100 of the teraflops. The real number is around 200 teraflops for one chip. And they also have the 100 megabytes on chip memory. This is much bigger compared with the latest GPU such as NVIDIA A100. And then it also have the off-chip memory for around a couple of terabytes. So this is the machine. This is the chip to support the SambaNova machine. So we call it SN1 RDU. And we also call it RDU for short. And so as we can see, this is the workflow of how to use the RDU. So if we have the deep learning workload and we want to run it on the real SambaNova chips, it will just put all the operations to the real hardware, and the data will flow from different chips, and it will save a lot of communication time. So it will be very high efficient for the compute and the memory access. And the just mentioned is just for one chip and one machine. So if you have the eight chips on one rack, it will call the quarter rack. It will include 8 SN10, and it will upgrade to a larger rack. It will call half rack. It will have 8 RDU in the half rack, and it also have the 4 SN10 8 in the full rack. So, and the memory is 90 times more than memory compared with the NVIDIA A100. So it will have a large scale for this system. But in our system, we have the 2 cards, and we have the half rack. So for this hands-on section, we will use the half rack. And also it will have a very good communication between different RDUs. So this is the architecture of how can you communication with the different RDU. So you can see they have 8 RDUs, and each RDU have the link. They call it RDU connect to the different RDU through the switch. And the bandwidth is almost around 100 gigabytes per second. And then it also have the RDU direct to connect to the memory. So you can see they have the full connector network, and it also have the RDU directed to the memory. So for this part, it have a very good communication ability. So I will talk something about the hardware. So for the hardware, it has a couple of layers. The first layer is if you have a model, they will give you algorithm layers. The algorithm layers will give you a low precision support, such as you can use the half precision or more than half precision for your model training or inference. And it will give you a sparsity, and you can use the sparsity to speed up your training. And it also have the compression to make your model much more smaller. And for the compiler, we have a global data flow compiler. So, and it also have a memory optimization to how to very high efficient to use the memory on the RDU. and it also have a very high efficiency mapping algorithm to map your real model to the real hardware. So this is the compiler, and this is the architecture. The architecture, they have the hierarchical compute and the configurable memory, as we said in the last slides, and it also have the data flow optimized communications between different PCU and PMU. And for the hardware, the VLSI, they have a very high performance implementations for the performance. And all of those compare with the very flexibility and the efficiency hardware for use for the SambaNova. And this is the much more high level architecture of the SambaNova software stacks. So as you can see, if you have a model, you can just write some PyTorch, very similar to PyTorch scripts for your model, and after that you can try the compiler will use the data flow graph analysis and to build the model to different operations, such as some customized operations and machine learning operations. And after that, they will use the optimizer and to map the operations to the real hardware. And it will have a different layout and to improve your performance. And after that, it will have a runtime to manage the operations with the real hardware. But the users just need to read the code from here above there. So you just need to write some code with different models, and the compiler will do all of them. And so this is the examples of how to map your CNN model or some ARM model or different DNA model to a real hardware on SambaNova. So this is the CNN model as example. We have different operations and different layers and different kernels. So for traditional GPU, they will map the operations to processors in such a time, so the communication will go through the memory hierarchy. It will be very time-consuming for the training. But for the SambaNova, it will map the operations to the real hardware from different error, and you can see the different error have different functions, and the data will just goes in from the conclusion one, and you will get the result from the sum operation. And the compiler will map the operations to the real hardware in time, and they will give you a very high performance layout to improve the memory access performance and the compute performance as well. So also the communication between the RD and in RDO between the PCU and the PMU will give you a very high performance for the communications. So the SambaNova eliminates the overhead and maximize the utilization of the memory access and the compute. Okay, so I already just a little bit about the precision. So the main idea of so on the SambaNova, they can support two kind of the data format. The first one is the Harvard precision. The Harvard precision is named the bfloat60. So this is the Harvard precision they use. They will have the one single bit and seven bits of the exponent and the 7 bits of the functions, and so 8 bits of the exponent and 7 bits of the functions. So this is used to speed up your DNA model and the training, and they also support the single precision. This is standard data format for the DNA training. So it also have the 1-bit sign, 8-bit exponent, and 23 bits of the functions. And but the main idea of the BF16 is to provide a short data format to speed up the performance, but it all have the shorter functions, which means it will lead to less accuracy of your model or of your computations. So when you want to use the BF16, you need to be very take care of the accuracy of the model, but it will give you a better training throughput. So, for most of the current DNA models, we can still use the half precision to speed up the performance, and then will maintain the same accuracy as the single precision. So you can, if you want to improve your throughput of your model training, and you could try the BF16 to speed up. They will need to 2 times speed up on training throughput with the same machine. And for the server bus, so I will introduce the hardware design of the server bus. This is the second hardware we used in our system. So the motivation of this hardware is for the current GPU approach, a lot of area are not used for deep learning, so they used it for some graphics. So the waste for DNA training, and the memory is far from the tensor core, some graphics cores. So it just have a very little on-chip memory, and the cache memory hierarchy is pretty long. So this is the microarchitecture of the GPU. So as you can see, it just have a very small cache for the L1 cache, and also the shared, and it also have a very multiple layers of the memory hierarchy. So it will take a long time to access the data, and the on-chip memory the bandwidth of on-chip memory is pretty low, and the off memory is much lower, and so the design of the design of the server bus is want to improve the bottlenecks of the current GPU to get better performance on server bus. So this is if you want to access the memory on the HBM2, so it will have a very long latency. So this is the hardware of the server bus. This is the server bus chip named the waffle-wise accelerators. So the chip is pretty large. It's about such. It's pretty large. So and it compared with the current largest GPU, the size of this chip is pretty large. So it's very difficult to design this chip, and they also have a lot of cores, and they can provide 18 gigabytes of the on-chip memory. So this is much bigger compared with the GPU, and the bandwidth is much higher, and the fabric bandwidth is much higher, and it will use the TSMC process, and so this is the hardware, and so in the next step, I will talk something about how can they improve the performance in terms of the compute and the memory access, both for the and also for the communications. So for the compute, so they have the fully programmable cores and the machine learning optimized extensions, and also they have the data flow architecture optimized for sparse dynamic workload. So as we can see, this is the micro architecture of the server bus chip. You have some on-chip memory in the core, and also have the different data flow in this core to control how the data workflow from the inside, and for the memory, they have a different approach to improve the memory access in the chip. So for the traditional memory architecture, it will share the memory from the computer from very far pass. So for this design, you can see this is a traditional memory architecture where if you want to access the memory, you need to go through the memory bus, and you will get the data from them. But for the server bus design, they distributed the memory across different cores, and you can just access the memory in a very short path. So for the server bus, the right answer to get very high performance memory access is to distribute high performance on-chip memory. So this is the architecture of that, and to improve the communications between different cores, they provide a very high bandwidth, low latency, cluster scale networking on chip, and it also full connectable to user-specific technologies. So based on this design, they can give you a very high efficient and high performance and communications between different cores. And this is the difference between the comparison between the server bus CS2 with the NVIDIA A100 GPU. So the chip size is 50 times bigger compared with the A100, and the core is much larger, 100 times bigger, and the on-chip memory is 1,000 times bigger. So this chip is much more expensive compared with the A100, but the performance is much better, and they will give you a much more on-chip memory to speed up your performance on memory access. And the memory bandwidth is much bigger because of the memory is on chip, so the bandwidth from different chip is much higher, and the fabric bandwidth is much bigger. So compared with the A100, so this design is much better if you just train the model on this chip. So for the software part, it has a couple of steps to run the models on real hardware. So it has 4 steps to run a model. The first step, you also support a different machine learning frameworks such as TensorFlow, PyTorch, and some others. And the first step is to extract and obtain the graph representation of the model from the frameworks and express it in templated forms. And the second step is to match the library to the real library from the server bus. And both of the kernels implemented on the server bus is high performance. And the third step is to place and route the kernels to the real hardware by the graph connectivity and the kernel performance function. And the last one is to link to create executable output that can load to run and run the CS2. So this is the briefly workflow of how to run a model on the CS2. And it as I said, so it also supports a lot of machine learning frameworks. So, and for the users, you just need to write some TensorFlow or PyTorch similar code to run your code on the server bus. So it doesn't require any specific knowledge about the hardware. So you can just use the TensorFlow and PyTorch and run it with any other knowledge of the CS2. And the CS server bus will integrate with the popular machine learning frameworks, and the researcher can just run the model, use the familiar tools. And also this is the workflow of the how can they run the DNA models and the machine learning algorithms on the servers. So the servers is the standard input to the server stacks. So it will extract the linear algebra graph representations of the models from the machine learning frameworks and translate it into LAIR. So this is the representing used in servers. So this is your model right in the TensorFlow and PyTorch, and after that it will compare with the different frameworks IR, and the different framework IR will convert to the servers IR, which the name is LAIR, and after that the LAIR can be run on the real hardware. So this is the workflow of the servers. So I left half hours for the hands-on section. So for the hands-on section, we have the system for the SambaNova and the servers. So for the servers, we have the 2 nodes, and each node has 8 RDU. So which means we can only run 8 jobs at the same time on servers. But we have 2 nodes, so we can run 6 jobs at the same time. So, and Carol also mentioned me, so maybe we can set up a pool or something to synchronize with each other to use the hardware. So okay, so if you have any question, just let me know. So we will use the BERT model for the hands-on section. So the BERT model is a transformer-based machine learning techniques to the language processing model, and developed it by the Google. And the BERT model has different kind of versions. The first one is the BERT base, and the second one is the BERT large. So we will use the BERT large as an example. And so you can check all of the scripts we will use from the GitHub repo. The path is the 03 AI Testbed. Okay, so I will continue to the hands-on section. Okay. So the first one, I will try to use the servers to train a BERT large model on the servers on 1 RDU, which is very similar to 1 GPU on the server bus. And we have a couple of steps to train that. So the first step is to log into the servers. So before you log into the servers, you need to have the ALCF user's account, and after that you need to set up the SDK environment, and after that you can copy the scripts from our path for the training and the inference. So and after that you can go to your path and run the training and the inference as well. So I will show how to do this. So the first step is to log into the Cerberus node. So you will try to access H2 this path and use the password from the mobile path plus.
Can I have permission denied when I try to copy on Cerebrus?
We can
Ignore it. I just ran through it. You can ignore refresh the README, basically. You can ignore some of them. It copies like most of that directory in the Cerebrus, but there's like one thing in there that doesn't copy out, it doesn't matter.
Gotcha.
Yes, we will come from the Cerberus first. And for the Cerberus, we have two nodes, but the second node is used for different workloads. So we can just use the Cerberus 2-01 for the testing. And for the Cerberus, we have 8 nodes. You can use any one of them. So I will use the first one.
It says permission delay if we copy for the Cerebrus.
For the Cerberus, permission delay.
It copies most of that directory, but there's one subdirectory that doesn't get copied. That's fine.
It works or no? So the second one is to copy the scripts from our press.
But you can't get transformers.
Yeah, there's no directory transformers.
Transformers is denied.
Yeah. Oh, maybe I'm in a special group or something. That's the fear.
I have it.
I think it's denied to Model Zoo -R 1.3, but just Model Zoo exists.
It's like there's 2 Model Zoo directories. I didn't design it.
Oh, okay. Got it.
So for my part, I just copy the data. Permission delay. So after the copy, you need to go to the model zone and the transformer. And for this example, we will use the TensorFlow as a framework and BERT model. So it has a couple of scripts for the training and the inference. So the only thing you need to do is to modify the data path to our real large databases in this YAML file. So just change the path to the data path to the real data path from from this YAM file. And the figure parameters birth large. So your two point in this change is to point the data directory to the software server bus dataset birth large MSL128 and also for the evaluation input as well. So after that, you can try to use the scripts in the GitHub repo. And the first steps is try to compile the models on the CPU side. So it will build the model to a couple of the modules that can be run on server bus. And the second script is used to run the modules on the server bus. So I will try to use the first one.
So Cerebrus uses Slurm, right?
What?
There's a job.
Yes, there's a job.
Okay, is it in CS run? Is that what controls like Slurm?
Yes, they will use the Slurm to try to run the jobs, and the first one is just for the compile, and the second one is for the run. So, but because the birth large is pretty huge, so it will take longer to compile the model and to run the jobs. And in this time, I can try to test the server bus, the SambaNova. It seems the SambaNova is done. So for the SambaNova, you need to log into the SambaNova using your ALCF user ID, and after that you can try to log into the SambaNova 01, or SambaNova 02, and after that you can try to source the environment from your local. And it will give you a SDK setup, and you can copy the scripts for the birth large from our path. This is our path, and after that you can try to run the birth large for the training and the inference. So I can check so I cannot check so not check because I cannot log into it. So I can log into the servers. So if you already download the birth large for the server bus, the scripts will be something like that. They will set the environment, so the source, and after that you will create the directory for the output, and link the data path to the output directory, and from this command, it will show how many RDU, which means how many devices you can use for the SambaNova, and after that it will compile the birth large and output some models, and this command will be used to run the modules on the SambaNova. And then this is the two commands are used for training, and the second two scripts commands are used for the inference. So if you can log into the servers later and try to run the scripts on that, you will see the throughput and the memory bandwidth with the output.
Oh, no. That happens all the time. Something goes down.
Yeah, something goes down, so we can just try to train the model on the servers. So, but because of the model is pretty large, so it will take a long time to get the output from them. So just let me know if you have any question for that.
So how long does the training run for?
And it will take a long time. So, but we can see the throughput shortly if we get the output from the compiling, so we get the throughput. But if you want to train a very large completely, it will take almost 1 or 2 days on that.
How difficult is to port from
4 cores on that.
like port from regular Python to run it on?
Yes, yes, the regular Python. So I will show. Yes, the code on the SambaNova and the servers is very similar to the TensorFlow and PyTorch. They support the TensorFlow and PyTorch, but a couple of interfaces will be different. So maybe sometimes if we want to port a model to the SambaNova or servers, we need to rewrite the code and use some specific interface to point out what kind of hardware we want to use, but it's very easy to use. Yes, and then they have, sometimes they have some tutorial to help us to how to port your models from the GPU to the servers or SambaNova, but they will be very quick.
So for the servers case, I'm trying to run scripts at step 3, run scripts. But I try to set the model directory equal to model directory and so on.
So yes, you need to for the
Error host name.
yes for the servers you need to change the model data directory to the to. Can you access to the GitHub repo?
No, the GitHub, I haven't tried that yet.
So for this part, you can try to access the GitHub repo. They will show you how to modify the data directory to our real ATPESC. So this is the only thing you need.
I did that step.
You did that step.
The model directory equal to model directory and so on. There's a dollar host name.
Mm-hmm.
The dollar host name. When I try to do that, locally,
Can I see the arrow from your side?
see here, I was, where's my cursor? Yeah, I was able to modify that config file, no problem. But when I try to set this variable model directory equal to model and so on.
Okay, so your host is
The host name is login 1.
host is 1, so you can just
Oh, export.
export the host name. Oh, okay, so and the host name is not available. So
Yeah, that's kind
yes, yes, I can give you a link to figure out the host name. It's okay. It works now.
Yeah, it works now.
Okay,
It's
so
host name.
Have some
There's
name.
no
Yes, no
underscore.
underscore. Okay.
Right.
Mhm. Yes, for the server bus, it will take a bit longer to get the output. So if you have any question, just let me know, and this system will be available in a couple of weeks. So I will end my part. So if you have any question, be free to send us email or just send us know. Yeah. Thank you.